Imagine a place in space where time slows to a crawl, light simply vanishes, and the normal laws of physics no longer apply. Most of us picture black holes as giant cosmic vacuum cleaners, sucking up everything in their path. But if our sun were replaced by a black hole of the exact same mass, the solar system wouldn't actually change that much. We would freeze in the dark without sunlight, but Earth would stay right where it is, continuing its normal orbit. The danger of a black hole isn't a vacuum effect. It's the result of extreme, localized density. If you took all the mass of the sun and squeezed it into a sphere only a few kilometers wide, the gravity becomes so concentrated that even light cannot move fast enough to escape. That boundary where the escape velocity exceeds the speed of light is the event horizon. To see what that looks like, we can follow a hypothetical astronaut as they approach and cross this specific line. Crossing the event horizon means leaving the observable universe permanently. It is a physical point of no return. From a distance, you would watch the astronaut slow down and fade to a dull red as they reach the edge. To you, it looks like they've frozen in place, never quite crossing over. But for the astronaut, everything feels normal. Their watch keeps ticking and their heartbeat is steady. Both observations are accurate because gravity is bending space and time itself. The closer you are to a massive object, the slower time actually moves relative to the rest of the universe. At the edge of a black hole, objective reality splits into two different physical experiences, depending on where you are. While crossing into a supermassive black hole might feel calm at first, falling into a smaller one is a different story. The gravity pulls harder on your feet than your head, stretching your body until it becomes a thin strand of particles. Scientists call this spaghettification. Eventually, all the matter that falls in is crushed toward the exact center, the singularity. We define the singularity as a point of infinite density, where an immense amount of mass occupies zero volume. But in physics, an infinite result usually indicates that our mathematical models have reached their limit and fail to describe reality. This is where our two best theories of the universe collide. Einstein's general relativity describes the gravity of the whole black hole, while quantum mechanics describes the tiny particles inside it. The problem is that these two sets of rules refuse to work together, leaving us with no confirmed way to calculate what actually happens at the center. This leads to the information paradox. If quantum physics says information can't be destroyed, but a black hole appears to erase everything that enters it, then one of our core understanding of the universe must be wrong. Reconciling these facts would require a new framework, the theory of quantum gravity. Without a complete theory, we're left with possibilities suggested by the math, like the idea that space could fold until two distant points touch, creating a wormhole shortcut through the galaxy. There's even a hypothesis that the matter collapsing into a singularity could be the seeds of an entirely new universe, separate from our own. Because the event horizon prevents any signal from escaping, we are currently barred from observing the truth behind these theories. Finding the missing pieces of physics required to describe the singularity will change how we define the relationship between matter, space, and time.